Hello and welcome again to my Physics Online video lecture series. Today's video I'm going to be doing a walkthrough example of a collision between a moving object like a disc or a puck and a stick, which will sort of like catch the object and such that the stick can rotate but not translate. Alright, so the criterion that we have here is essentially along the lines of that I have a stick which has maybe a peg that it can rotate about, but that keeps it from sliding. Okay, so before we get into the example, worth recalling sort of the background information to this video. This is part of the series of videos I've been making about rotational dynamics and specifically collisions between extended objects, extended body objects. So in some sense it's worth recalling the relevant conservation laws. This includes energy, linear momentum, and angular momentum. The main thing for energy is that the kinetic energy is 1/2 the mass times speed squared plus 1/2 the moment of inertia times omega squared. Linear momentum is given by P is equal to m times v. Angular momentum is L equals R cross P, or in other words, R cross V times mass m. So these are the three things that could be conserved. The relevant conservation law, this is no net torque on system. So no net torque on system. This one, no net force on system. And by saying no net on system, we mean no net external torque or force to have this conserved. This one is if elastic, and that's basically all that we can say here, because there may not be any net work done on the system. But for example, if one object crashes into the other and damages or dents it, then there's some internal work that will take some of the mechanical energy out of the system. All right, so for the example that we want to do today, the other part of the thing is that we should identify what kind of collision. So that means we are looking at what kind of constraints do we have on the system. Are both objects free to move? Are they both free to translate? Are they both free to rotate? So that helps figure out collision type. Do we know whether it's elastic or not? Elastic, perfectly inelastic, etc. Is another important constraint to consider. And then, of course, the other bit to all of this is we need to identify where axes of rotation are, where moments of inertia are, etc. First, we have to identify where the axis of rotation is in order to then calculate the moment of inertia or relevant moments of inertia about that axis. All right, so let's consider an example. And in this example, I know there's a lot of text to it. Basically, you have a 2-meter long rod which is lying at rest on a frictionless surface. There's essentially a peg through the middle of the rod so that the rod can rotate freely. So basically you have a rod like this and it's allowed to do this motion freely. It just can't do this motion or anything like this. You have a disc, a very small disc, which hits the rod midway between the peg and the end of the rod. And given the masses of both and given the initial speed of the disc and being told that the disc reflects at 12 meters per second in the other direction, starting with 24 meters per second one way and then 12 after the collision, we want to know what the rate of rotation of the rod is and whether energy and linear momentum are being conserved in this example. The first thing that we ought to do in solving this problem is draw for ourselves a few diagrams. This is a point that I've discussed before in my previous videos and lectures, and it's one that I will probably discuss again many times in the future. So let's begin by drawing ourselves some diagrams. What we want is actually a before diagram and an after diagram. So this is the before diagram. This is the immediately after diagram. And I'm actually going to label certain things that are common between the two diagrams on one or the other, but not both. Specifically, we want to know what our axis of rotation is, and therefore we need to know what the value of r is for figuring things out. And so, like, this is the axis of rotation. It's the same here as here. R, for the purpose of figuring out angular momentum about that axis, would be this red vector to the disk. For the rod itself, R is is basically just to the center of mass. But we would use the moment of inertia about, again, this axis of rotation. And so, in some sense, what we've done here is we have identified where is the axis of momentum and what do we need to figure out for moments of inertia. Before I go on to solving this problem, a thing to note. In order for this linear momentum conservation to occur, immediately before, immediately after, we would need to have a center of mass motion for this stick or this rod. Do we have such a thing? The answer is no. The peg is holding the center of mass in place. That means that momentum is, or linear momentum, is not being conserved here. I want to draw a quick pair of sort of like counter examples for what, like a pair of counter diagrams before and after for what would need to happen for linear momentum to be conserved. But this is kind of an aside for the purpose of actually solving this question. If the peg is not in the dead center of mass of the rod, then that means that when the rod is rotating, the center of mass is in fact moving, and so there will be some center of mass velocity. Specifically, I would now need to label two different values of r. One of them would be like r for the center of mass, and the other one would be r for the location of the disk, so r disk. And this v center of mass, in this case, immediately after impact, though beyond that, the peg is exerting a force, so not continuing thereafter. But immediately after impact, I would have v center of mass final is equal to r center of mass times omega. And so this is non-zero, which means that before to after the impact, it would be possible to conserve linear momentum. However, the case that we actually have, the v center of mass is 0 because r center of mass up here, the equivalent of this r center of mass term, is 0 since the center of mass and the axis of rotation are 0. This means that we have basically answered one of the problems posed here. So now that we've done that, we can go to actually solving for the final angular speed. And it's worth noting that we have at this point actually defined for ourselves a few of the things that we needed to do to solve this problem. Remember that we said, okay, we need to identify collision type, constraints, free to translate, rotate, etc. The answer is it's not free, the rod is not free to translate, that is a constraint. The collision may or may not be elastic, we don't know yet. We've identified our axis of rotation, and therefore we've identified the relevant distances for figuring out moments of inertia. All right, we know that angular momentum is going to be conserved because if we come back over here and look at relevant forces, I could draw forces here at the moment of impact. There's some force from the disk on the rod, there's some force from the rod on the disk. They are in opposite directions. They are equal magnitude because it's a Newton's third law pair. So this one would be r disk, rod. This would be force, rod, disk. Newton's third law says that these two things are equal magnitude, opposite direction. And as far as torques are concerned, we have to look at the relevant axis of rotation and distance from that axis. Since that's the same for both of these forces, the two torques are also equal, but in opposite directions. So torque of disk rod is equal to torque of rod disk. And since those are the only torques present because the only other force is at the axis of rotation, so torque peg is equal to 0 in this case because it's at the axis of rotation. It follows that the net torque for the system is 0. Therefore, we have angular momentum conservation. With the axis of rotation being the peg's location, we can therefore define for ourselves a few further points. One of them being that distance r that we need is actually a quarter of the length of the stick. How do we know that? Going back to this original paragraph, we are midway between the rod's end and its center. That means that r is L/4 from the peg. That's where the disc is colliding. So that's how we know that piece of information. Second piece of information, how do we calculate the moments of inertia? Or do we need to? Well, for the disc, we are basically acting like we have a point object. So it's a point-like object, meaning that the radius of the disc is small compared to the length scales implied. And so what this means is that the moment of inertia for the disc, both in the before and after case, is equal to m times r squared. And so this means that I can also just simply calculate the angular momentum. I can either call it mr squared omega, or I could simply use m disk times r times v disk. And we again note that there is an initial and a final for the v disk. For the rod, our moment of inertia is necessary because it's an extended object, and so our angular momentum is moment of inertia I times omega. And since it is a thin rod with the axis through its center, you can go look in my previous videos, or you can look it up in a textbook, whatever textbook you're using, be it OpenStax or whatever. You'll find that this moment of inertia is 1/12 of the mass of the rod times the length of the rod squared. Okay, so that is our moment of inertia, and therefore this is our total angular momentum. All right. Conservation of angular momentum basically says that before is equal to after. It's worth figuring out what direction everything's going in. This right here can be represented as positive because the thing is spinning in the counterclockwise direction. The disk actually reverses direction. So L disk initial represents plus mass of disk times r times v disk, which by the way is plus mass disk times L/4 times v disk initial. The L disk final, the angular momentum final for the disk, since it is moving in the opposite direction, becomes negative mass of disk r v disk final. So that is negative mass of disk times L/4 times v disk final. Now let's put this equation, and this equation together. And what we end up with is mass of disk times L/4 times v disk initial is equal to the 1/12 of mass of rod length squared of rod omega minus mass of disk L over 4 times V disk final. Now we want to combine like terms as best we can. What that ends up giving us is that we have 1/12 times the mass of the rod times the length squared of the rod omega is equal to, and noticing that we have an MD L over 4 for both of these terms, we just collect those outside, so mass disk L over 4, and what is being associated with those two is V initial for the disk minus V final for the disk. Okay, so now I want to solve for omega. I divide both sides by 1/12 MR L squared. So that is 12 M disk L divided by 4 M rod L squared times V disk initial. I have a little typo here. It's V disk initial plus V disk final, because again, I have to add this term right here to both sides, not subtract it. Okay. I can cancel one of the L's. So this L cancels with the squared part of this L. I have a 4 here and I have a 12 here, which can cancel to a 3. And I can plug my numbers in, which I get from the paragraph in here. Mass of disk. So this would be mass disk. This would be mass rod. The half its initial speed is telling us that V final is 12 meters per second. The initial speed of the disk is V initial 24 meters per second. So we can go, and 2 meters is the length of the rod, which is given explicitly in terms of its symbols. So I have 3 times mass of disk, which is 0.5 kilograms, times this sum, which is 24 meters per second plus 12 meters per second, divided by mass of rod, which was 4.5 kilograms, times length of rod, which is 2 meters. Plugging all my numbers in, I end up getting that omega is 6.0 radians per second. So I've solved for the final angular speed of the disk. This final rate of rotation is my omega. The last part is this question about whether or not energy is being conserved. So initially, K initial, I have 1/2 mv disk initial squared. This is mass disk. So that is 1/2 times 0.5 kilograms times this initial speed, 24 meters per second squared. That ends up giving me a total of 144 joules. My final should be 1/2 I rod omega squared plus 1/2 mass disk V final disk squared. So I'm looking at 1/2 of, and then this term again was 1/12 of the mass of the rod times the length squared of the rod times the omega squared, and then that is added to this other term. Alright, so we're ready to plug our numbers in to the equation to get the final kinetic energy. So this is 1/24 of 4.5 kilograms times 2.0 meters squared times 6.0 radians per second squared, to which we're adding 1/2 of 0.50 kilograms times 12 meters per second quantity squared. Okay, this term right here ends up being excuse me, 27 joules. This term right here ends up being 36 joules, and so my total final kinetic energy is 63 joules. So if my final is 63 joules and my initial was 144 joules, then it follows that energy has not been conserved in this collision. Now that in turn could be one of two things. Either energy was not conserved because some work has been done by the peg on the rod, or more likely energy was not conserved because we had an inelastic collision. The rod and or the disc were somewhat dented, a sound was made during the collision, etc. Alright, well that's it for this example, and that's all I'm doing in today's video. It is already pushing kind of the limits of what we would call a short video. These examples do tend to be pretty long when you're getting into extended body collisions. So hopefully you enjoyed having a long, fairly thorough video walkthrough. And in any case, I hope that you learned something from today's video. And as always, thanks for watching.